question. What did one girl firefly say to the other girl firefly? You glow, girl!
First thing we're going to talk about is sigma notation. That's the sum of n terms, a sub 1, comma a sub 2, comma dot dot dot, all the way till a sub n, written as this right here. This sigma stands for the sum from I equals 1, I is your index of summation, and 1 would be your lower bound of summation, to n. And n is your upper bound of summation. And you're taking the sum from I equals 1 to n of a sub I. And that's why you start at a sub 1, because you plug in that 1 for I right here, and that is your first term. And then you add, because it's the sum, your next term, which would be a sub 2, plus your next term, which would be a sub 3, plus dot dot dot, all the way until you get to a sub n, which is your last term. You can see how that works over here. We have the sum from I equals 0 to 3 of 3 to the ith power. That means you start with 3 to the 0 power. Add that to 3 to the first power. Add that to 3 to the second power. Add that to 3 to the third power. And we keep going until, oh yeah, 3 is our upper bound of summation. So the last thing we should plug in for I is going to be 3. So once we get there, then we're done with our sequence. So we need to then add up these numbers, 3 to the 0 plus 3 to the first plus 3 to the second plus 3 to the third, and we get 40, which is what this right here is equal to. Same thing here, except this time we have the sum from m equals 0 to 2 of the quantity m plus 2. So we're going to start by plugging in that 0, and we get 0 plus 2 plus 1 plus 2 plus 2 plus 2. And then we look, 2 is our upper bound of summation. That's why we stop right here. Now we have our sequence, so we add all of these together and we get our answer over here. Now let's talk about approximating area under a curve with rectangles. So there are 3 different ways we're going to approximate area under a curve with these rectangles. The first is a left endpoint approximation or a left-hand approximation. The second would be a right endpoint or right-hand approximation, and the third would be a midpoint approximation. So as you can see, these rectangles are broken up based on subintervals, and those subintervals are going to be the base of each of those rectangles. Now the height is the only thing that's going to be different for each of these rectangles. The subintervals, these bases for each rectangle, should be the same whether it's a left endpoint, right endpoint, or a midpoint approximation. However, the height will be determined based on whatever type of approximation it is. If it's a left endpoint approximation, you're going to look at one of your subintervals, let's say from a to x sub 1, and in order to determine the height, you take the left endpoint of that subinterval, plug it into the function, and whatever you get for your corresponding y value, that's going to be the height of your first rectangle. And that's how you do a left endpoint approximation or left-hand approximation. A right endpoint or right-hand approximation says that you take that first subinterval, and what you're going to do is you're going to take the right endpoint of that subinterval, x sub 1, plug it into your function for x, and get the y value that goes with it. Now that y value is going to be the height of your first rectangle. Now see how it's different. The left endpoint being the height of your rectangle and the right endpoint being the height of your rectangle. And it works the same for every subinterval after that. You look at the given subinterval, you take the right endpoint and plug it in the function to get the height of your new rectangle, or you take the left endpoint if you're doing left-hand approximation and plug it in the function to get the height of your rectangle. The midpoint approximation means that you have to take the midpoint of your subinterval, plug it in the function for x, and that will get you the height of your given rectangle. Now let's talk about the left-hand approximation a little bit more. This is what it looks like in sigma notation. Okay, this means the sum from I equals 1 to 5 of f of lowercase m sub I times delta x. Now, what does that mean? Well, I is going to represent your index. That indicates which subinterval you're on. So here we have 1 subinterval, 2 subintervals, 3 subinterval, 4, and then 5. Now, the m is going to represent which x value you're going to plug in. And we said if you're using a left-hand approximation, you're going to plug in the left endpoint for each of these subintervals. So on this first subinterval, you would plug in this x value. On this second subinterval, you would plug in this x value. On your third subinterval, you would plug in this x value. Fourth subinterval, you would plug in this one, and then fifth, you would plug in this guy. Now, you plug them in to the function to determine the height of your given rectangle. And that is going to be what this f represents. When you plug in your x value to the function, that will give you the height of your given rectangle. So this represents the height of your given rectangle. So your first first rectangle here actually has no height. The second one has a height that corresponds with this x value right here when you plug it into the function. The third rectangle has a height right here. Fourth rectangle has a height right here. And then fifth rectangle, its height is right there, right? And you can see that those heights correspond to the left endpoint x value. Now, the delta x is just going to be the distance between the x values. That's going to be the base for each of your rectangles. And we said to determine delta x, you're going to use b minus a over n. That formula will get you the length of each of these bases. And it should be the same for each of your rectangles. Okay, so here is your first one, second one, third one, fourth one, and fifth one. And you can see each of the rectangles has the exact same base. Now a right-hand approximation works the exact same. The I represents the index, which interval you're going to be on, and your uppercase M this time represents the x value, and it's going to be the right endpoint of each of your sub-intervals. So if we're looking at each of these sub-intervals, to get the height of your given rectangle, you are going to plug in the right endpoint, the right x value, instead of the left one this time. And to ensure that you do this correctly, I would, instead of starting with 0 to 4/5, I would start with 3 1/4 to 4 as your first interval that you choose. Because what you're going to do is you're going to make sure that you start with the rightmost endpoint. You're going to include the furthest point on your interval, which would be 4. That's going to be the first x value that you plug in, and that will get you the height of your first rectangle. Next, you go to your second subinterval over here and you plug in your right endpoint to determine the height of your rectangle. Then you plug in this one, and this one. We're not plugging in 0 because we are using the right endpoints. Just like last time we didn't plug in 4 because we used all of the left endpoints. Now, f again represents the height of each rectangle. When you plug in those given x values, you get the corresponding y values that determine the height of your rectangle. And the delta x, just like last time, is determined with b minus a over n. That's going to be the base of each of your rectangles, and it should be the same length. The midpoint approximation, only difference here is that instead of plugging in a left endpoint or right endpoint, you're plugging in the midpoint on the interval, which gets you kind of an average of the y values for the given interval. So the I, again, represents which interval you are on. So either the first, second, third, or fourth. This one only has 4 intervals this time. The midpoint right here means that you are going to plug in the x value, which is the midpoint on your given subinterval. So if we're looking from 0 to 1, you would plug in this x value, 1/2, to determine the height of that given rectangle. Same thing here. You would plug in 1.5 to the function to determine the height of your given rectangle here. You would plug in 2.5 to your given function to determine the height of this rectangle, and then you would plug in 3.5 to determine the height of this given rectangle. And again, f of your midpoint represents the height of your rectangle. That's the y value that the function is at that given x value. The delta x you get by doing the exact same thing, b minus a over n. That does not change. Make sure that your delta x is always going to be the exact same for each of your sub-intervals. Now I want you to see what this looks like when we write it out. You know that you are going to have 5 sub-intervals for each of these approximations for areas under the curve. You have a left-hand approximation and a right-hand approximation, or left endpoint and right endpoint. We have 5 sub-intervals, therefore you have 5 rectangles that you need to find the height of. Now this first rectangle over here has a base of 4/5, and the height corresponds with the y value of the function at x is equal to 0. That's why it's 0/5. This rectangle right here has a base of 4/5, just like each of these do. And the height corresponds with the left endpoint on that subinterval, which is 4/5. So I plug 4/5 into the function, and I get the height that goes with that rectangle. That's why this gives you the area of this rectangle. The area of this rectangle is found by doing 4/5, which is the base, times the height, which corresponds with the left endpoint, which would be 8/5. When you plug that into the function, you get the y value, or the height of your given rectangle. That's why this is base times height. So this gives you the area of this rectangle, and so on for each of these. The only difference over here is that instead of plugging in the left endpoints for each of these rectangles or these subintervals, I'm plugging in the right endpoints. So to get the height of my first rectangle, I plug in 4/5 to the function to get the height that goes with that rectangle, right? So 4/5 is the base for each of these. And then for the first rectangle, the height is f of 4/5, the function at 4/5. For my second rectangle, the height is going to be f of 8/5, which is the right endpoint of that interval. For my third rectangle, the height is going to be f of 12/5, the function when I plug in 12/5. That will give me the height of my third rectangle, and so on. Now, as you can see, when you have a lower sum approximation or an upper sum approximation, an underestimate or an overestimate, and you can see because it's over the graph, it's an overestimate, because it's under the graph, it's underestimate. As you create more and more rectangles, as the number of subintervals approaches infinity, you are going to get the exact area under the curve. And that's what we're going to talk about right now. The limits of lower and upper sums says let f be continuous and non-negative on the interval a to b, and the limits as n approaches infinity of both the lower and upper sums exist and are equal to each other. That is, the limit as n approaches infinity of s of n is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of lowercase m sub I times delta x, which is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of uppercase m sub I times delta x, which is equal to the limit as n approaches infinity of uppercase s of n. All this is saying is that your underestimate or your overestimate are all going to be equal to each other as long as n approaches infinity. The number of subintervals, the number of rectangles approaches infinity. That's going to get you the exact area under the curve. Now, the area of a region in the plane says let f be continuous and non-negative on the interval a to b. The area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x, where x sub I minus 1 is less than or equal to c sub I, which is less than or equal to x sub I, and delta x is equal to b minus a over n. So all this says is just exactly what we were talking about. If we have an interval from a to b and vertical lines cutting off the area under the curve at x equals a and x equals b, then in order to get the exact area under the curve, what we'd have to do is create an infinite amount of rectangles under this curve, where the height of each of those rectangles is denoted by a different x value, which would be the c sub I, and delta x represents the base of each of those rectangles. Then if we were to create an infinite amount of those rectangles and add them all together, we would end up getting the exact area under the curve. Now let's look over the guide to approximating with Riemann sums. And Riemann sums are just approximations with rectangles for the area under the curve. So first thing you're going to do is determine the base of each rectangle using b minus a over n. And a and b just come from the interval that you are finding the area under the curve on. A is the beginning of that interval, b is the end. Then you're going to plug in either the left or the right endpoints or the midpoints to find the height of each rectangle. And you plug in those left, right, or midpoints to the function to find the y values that go with that, and those will be your heights of each of the rectangles. You can then find the area of each rectangle and add the areas together to get your approximation. To determine whether it's an over or underestimate, you just need to memorize this. If it's an increasing function, a left-hand approximation will give you an underestimate. A right-hand approximation will give you an overestimate. If the function is decreasing, a left-hand approximation will give you an overestimate, while a right-hand approximation will give you an underestimate. Lastly, the midpoint approximation is not based on increasing or decreasing functions. It's actually based on concavity. So if a function is concave upward, a midpoint approximation is going to give you an underestimate. Concave downward will then give you an overestimate if you use a midpoint approximation.
Try not to bug out. It's example time.
Now, example 1 says use left and right endpoints and the midpoints to find 3 approximations of the area of the region between the graph of the function and the x-axis over the given interval. So here's our function, y is equal to x squared. You can see it graphed over here. Our interval from a to b is from 0 to 2, and the number of subintervals, or the number of rectangles we're going to use, is 4. Now, we're going to start by finding our left-hand approximation, or left endpoint approximation. To do this, we need to recognize that we are finding the area of 4 rectangles and adding them together to approximate the area between the x-axis and our function from 0 to 2. So this little region down here. Now, to find the area on the curve using 4 rectangles, we need base and a height for each of these rectangles. The base is going to be the same. We find that by using our formula, delta x is equal to b minus a over n. And we said our a value is 0, our b value is 2, and our n, the number of subintervals, is going to be 4. We plug those in, we simplify, we end up getting that the base of each of these rectangles is going to be equal to 1/2. This is also going to be the length of each of our subintervals. Now, the subintervals, we're going to use those and look at the endpoints of of those intervals in order to find the height of each of our rectangles. So to determine the height of each of the 4 rectangles, let's look at our first rectangle. That's going to be on the interval from 0 to 1/2 because that's the base of our first rectangle. The base of our first rectangle goes from 0 to 1/2. Now, we're using a left endpoint approximation, which means we are going to plug in the left endpoint of that subinterval to our function. So the left endpoint of this subinterval from 0 to 1/2 is going to be 0. We plug that in the function and we end up getting a height of our first rectangle of 0. So that means that our first rectangle is going to have no area. The second rectangle goes from 1/2 to 1. We are going to plug in the left endpoint on that subinterval, 1/2, to the function, and we end up getting a height of our second rectangle as 1/4. And you can see it's because the function y equals x squared at x is equal to 1/2 is equal to 1/4. That's how high our rectangle goes. Now our third subinterval is going to go from 1 to 1.5 or 3/2. Again, we are going to plug in our left endpoint, which is going to be 1 on that interval, to the function to figure out the height of our third rectangle, and 1 squared is just 1. So the height of our third rectangle then is going to be 1 unit. So we go up 1 and create our rectangle going from 1 to 1.5. Now our last rectangle goes from 1.5 to 2, and on that subinterval the left endpoint is 1.5. We have to plug that into the function to figure out our height, and that's going to be 9/4. So our last rectangle is going to have a height of 9/4, so it goes up to 9/4. We have our last rectangle. Now, in order to figure out the area of this purple region, what we have to do is take our base for each of these rectangles and multiply it by the height. So the base is the same, so it's going to be 1/2 times 0 plus 1/2 times 1/4 plus 1/2 times 1 plus 1/2 times 9/4. You could also just add together all of the heights and then multiply that quantity by 1/2 because it's the same thing, right? We just factored out a 1/2. Either way, you end up getting a area of 1.75 square units or units squared, and that is going to be, because this function's increasing and it's a left-hand approximation, it's going to be an underestimate. Part 2 of this, we are going to do a right endpoint approximation. Again, we have 4 rectangles that we are trying to find the area of and add together to approximate the area between the x-axis and the function. The base is going to be the exact same. Delta x equals b minus a over n. And again, b, a, and n are all the same, therefore you are still going to have a base of 1/2. This means that the length of your subintervals is also going to be the same. The only difference is going to be the height of each of those rectangles. You could start over here and choose the right endpoints this time, but I always like, if you're doing a right endpoint approximation, to start at the right end of your interval. So I'm going to start on this side of the interval to make sure I only choose the right endpoints. So I go from 1.5 to 2. And because it's a right endpoint approximation, I'm going to plug in 2 because it's my right endpoint. I plug that into the function and I end up getting the height of my rectangle over here, which is going to be 4 units. So I go up 4 units. There you go. Done with that first one. The second one goes from 1 to 1.5. I take the right endpoint, 1.5, plug it into the function for x to determine the height of that rectangle, and end up getting 9/4. So I draw that rectangle now. That goes up to 9/4 and has a base of 1/2. My third rectangle goes from 1/2 to 1. I'm plugging in the right endpoint, so I plug in 1 to the function. I get 1 when I square that, and that's going to be the height of my third rectangle. Height of my fourth rectangle over here, subinterval is from 0 to 1/2. I plug 1/2 in. That's the right endpoint of that subinterval, and I end up getting a height of 1/4. That's going to be the height of my last rectangle. Now, to get the area of this blue region, the right-hand approximation of this area under the curve, I have to multiply base times height for each of these rectangles, 1/2 times each of the heights, add them together. I could also just add together all of the heights and then multiply by 1/2. Either way, I end up getting 2.75 square units or units squared as the area of this blue region, which is an approximate area under the curve. Now, is it an over or underestimate? Because the function's increasing and I'm using a right-hand approximation, it's going to be an overestimate. Now, lastly, we need to do a midpoint approximation. So all that's different here, again, we have 4 rectangles that we're trying to find base times height for, and then we add up areas of the rectangles to get our approximation. The base is going to be the same. Delta x is equal to b minus a over n. A and b and n are going to be the same, so your base is still 1/2 for each of the rectangles. And that is also the length of each of your subintervals. The only difference is that the value that you're plugging into the function to figure out the height of your rectangle is not going to be the left endpoint or the right endpoint. It's going to be the midpoint of each of your subintervals. So for that first subinterval from 0 to 0.5 or 1/2, I am plugging in the midpoint, which is 1/4 to the function. If I plug in 1/4 to the function, I get 1/16, which is going to be the height of my first rectangle. It still has a base of 1/2, but now has a height of 1/16. The second subinterval goes from 1/2 to 1. The midpoint of that subinterval is 3/4. I plug that into the function. I end up getting 9/16, which is going to be the height of my second rectangle. Still has a base of 1/2, but has a height this time of 9/16. The third subinterval goes from 1 to 1.5. Midpoint of that subinterval is 5/4. I plug that in the function. I get 25/16, which is going to be the height of my third rectangle. The height of my last rectangle is determined by the midpoint, which here is between 1.5 and 2. That's going to be 7/4. I plug that into the function, and I end up getting 49/16, which is going to be the height of my last rectangle. Now, in order to get the approximate area using the midpoint approximation, I get base times height for each of these, which is 1/2 times 1/16, 1/2 times 9/16, 1/2 times 25/16, and 1/2 times 49/16. That's base times height for each of the rectangles. I then get an approximate area under the curve of 2.625 units squared. Now, when you're using a midpoint approximation, if you want to determine whether it's an over or underestimate, you look at concavity. Since this is concave up, this is going to be an underestimate. Example 2, doing the same thing. First, left endpoint approximation. We, this time, have 6 rectangles that we are going to use to approximate the area under the curve between 2 and 5. So between x equals 2 and x equals 5. We are going to use 6 different rectangles. That means we have the area of 6 different rectangles that we have to add together to get that approximate area. Now, the base is going to be the same. We find that by using our formula, delta x is equal to b minus a over n. A is 2, b is 5, n is the number of subintervals, which is number of rectangles, which is 6. So we plug those in, we end up getting 3/6, which again is 1/2. Now, that's the length of each subinterval. So let's go ahead and start determining the height of these rectangles. Look at my first subinterval, going from 2 to 2.5. I need to plug in my left endpoints because I'm using a left endpoint approximation. So I plug in 2 to the function in order to get the height of my rectangle, which is going to be 5. So the height of my first rectangle is 5 units. My second subinterval goes from 2.5 to 3. I plug in the left endpoint, which is 2.5, to the function to get the height of my second rectangle, which is 9 units. My third subinterval goes from 3 to 3.5. I plug in the left endpoint, which is 3, and I get a height of 14 units for that particular rectangle. My fourth rectangle, or fourth subinterval, goes from 3.5 to 4. I plug in 3.5 because that's the left endpoint on that subinterval, and end up getting a height of 20 units for that rectangle. For my fifth rectangle, it has a subinterval that goes from 4 to 4.5. I have to plug in the left endpoint, which is 4, to the function to get my height, which is going to be 27 units. Now, my last subinterval goes from 4.5 to 5, and I plug in my left endpoint, which is 4.5, to the function. I get a height of 35 units. Now, all I have to do to figure out the approximate area under the curve between 2 and 5, I'm going to have to find the area of each of these rectangles and add them together. So 1/2 times 5 plus 1/2 times 9 plus 1/2 times 14 plus 1/2 times 20 plus 1/2 times 27 plus 1/2 times 35. Add up all those, and I end up getting 55 units squared, or square units. Now, since this function is increasing, and it's a left endpoint approximation or left-hand approximation, I know it's going to be an underestimate. Now, with the right endpoint approximation, I'm doing the exact same thing. I have 6 different rectangles that I have to try to find the area of and add together. I need the base first for each of those. Base is determined using the formula delta x equals b minus a over n. B is the same, a is the same, n is the same. Therefore, it's still going to be a base of 1/2 for each of these rectangles. The height is the only thing that's going to be different. And since I'm using a right endpoint approximation, I start with my right endpoint. That's going to be 5. That ensures that I know that this I'm going to have to plug into the function. So I go from 4.5 to 5 as my first subinterval. I know that I have to plug in the right endpoint, so I plug in 5 to the function and end up getting 44 as my height for that rectangle. My second subinterval goes from 4 to 4.5. I have to plug in the right endpoint, which is 4.5, to the function. I get a height of 35 units. My third subinterval goes from 3.5 to 4. I have to plug in 4 because it's the right endpoint on that subinterval. I end up getting a corresponding height of 27 units. For my fourth rectangle, I go from 3 to 3.5. I have to plug in 3.5 because it's the right endpoint on that subinterval. The height that goes with that then is going to be 20 units. For my fifth subinterval, I go from 2.5 to 3. I have to plug in 3 because it's the right endpoint, and I end up getting a corresponding height of 14 units. Last but not least, from 2 to 2.5, I have to plug in the right endpoint, which is 2.5, and I get the corresponding height there is going to be 9 units. Now, to determine the approximate area under the curve, using a right endpoint approximation from 2 to 5, find the area of each of these rectangles and add them together. So 1/2 times 44 plus 1/2 times 35 35, plus 1/2 times 27, plus 1/2 times 20, plus 1/2 times 14, plus 1/2 times 9. I end up getting 74.5 units squared, or square units. Now, because this function is increasing and it is a right endpoint approximation, this is an overestimate. Now, I am going to do a midpoint approximation. So, again, 6 rectangles. Determine the base for each rectangle. It's the same. Delta x is equal to b minus a over n. Because those are all the same, it's still going to have a base of 1/2. The height is the only thing that's going to be different for each of these rectangles. My first subinterval from 2 to 2.5, I have to plug in the midpoint, which is 2 1/4, or 2.25. And I end up getting this approximate height for that rectangle. My second subinterval goes from 2.5 to 3. That means I have to plug in 2.75, or 2 3/4 to the function for x in order to find the height that goes with that, which is 11.375. Third subinterval, 3 to 3.5, I have to plug in 3.25, or 3 1/4 to the function. I get 16.875 as the height of my third rectangle. Fourth rectangle goes from 3.5 to 4. Midpoint is going to be 3.75, or 3 1/4. I end up getting a corresponding height of 23.375 when I plug that into the function. Now, fifth rectangle goes from 4 to 4.5. The midpoint of that subinterval is going to be 4 1/4, or 4.25. Plug that into the function for x. I end up getting the corresponding height, which is 30.875. Last but not least, 4.5 to 5. The midpoint of that is 4.75, or 4 3/4. Plug that in the function. I get 39.375 as the height of my last rectangle. Now all I have to do to approximate the area under the curve from 2 to 4 using the midpoint approximation is find the area of each of these rectangles and add them together. So to find the area of each rectangle, I'll do base times height, 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 and add them together, and I end up getting an approximate area under the curve of 64.375 square units, or units squared. Now, because I'm using midpoint approximation, I look at concavity. The graph is concave up, therefore this is going to be an underestimate. Now, example 3, we have y equals cosine of x, and we're going from 0 to pi over 2, and we want 4 rectangles. So, doing the same thing. First, left endpoint approximation. We have 4 rectangles that we need. And that's b minus a over n. That would be pi over 2 minus 0 over 4, which is going to be pi over 2 over 4, which is pi over 8. That means that the base of each rectangle is going to be pi over 8. Now, to determine the height of each of the 4 rectangles, I'm using a left endpoint approximation. So my first subinterval goes from 0 to pi over 8. I use the left endpoint, which would be 0, to determine the height of this rectangle. So if I plug in 0 to my function, which is y equals cosine x, if I plug in 0 for x, I get y equals cosine of 0, which is 1. That would mean the height of my first rectangle is actually 1. If I look at my second subinterval, I go from pi over 8 to pi over 4, plug in my left endpoint to the function pi over 8, get approximately 0.924. That's going to be the height of my second rectangle. Height of my third rectangle is based on my left endpoint of this subinterval, which is pi over 4. So I plug in pi over 4 to cosine, I end up getting rad 2 over 2. That's going to be the height of my third rectangle. And the height of my fourth rectangle, since my subinterval goes from 3 pi over 8 to pi over 2, I plug in my left endpoint, which is 3 pi over 8 to the function. I end up getting approximately 0.383. That's going to be the height of my fourth rectangle. Now, to get the approximate area under the curve, I take the area of those rectangles, add them together, simplify it. I end up getting approximately 1.183 units squared. That gets me the approximate area under this cosine curve from 0 to pi over 2. Is this an over or underestimate? You can kind of tell based on looking at it. This is an overestimate. And that's because the function is decreasing on the interval and we used a left endpoint approximation. Now we're going to look at the right endpoint approximation for this. We again find the base by using b minus a over n, which is still pi over 8. We then find the height that corresponds with each of these 4 rectangles. So we start with our first subinterval. Since it's a right endpoint approximation, I start with my rightmost endpoint, pi over 2. The height that corresponds with pi over 2 is actually 0. So the height of my first rectangle is actually 0. The height of my second rectangle corresponds with the right endpoint on that subinterval, which is 3 pi over 8. So I plug that in cosine. I end up getting approximately 0.383. That's going to be the height of my second rectangle. Height of my third rectangle, based on the right endpoint of my third subinterval, which is pi over 4. Cosine of pi over 4 gives you rad 2 over 2, so that's going to be the height of my third rectangle. Height of my fourth rectangle, then, I have my subinterval go from 0 to pi over 8, so I use the right endpoint, that's pi over 8. Plug it into my function for x, I get the cosine of pi over 8 is approximately 0.924. That's going to be the height of my fourth rectangle. Then to get the approximate area in the curve, I need to add together the area of each of those rectangles. So it's going to be pi over 8 times 0, pi over 8 times 0.383, pi over 8 times rad 2 over 2, and pi over 8 times 0.924. That'll give me the area of each of those rectangles, which is approximately 0.791 units squared. Now, is this an over or under estimate? You can kind of see it is an underestimate because the function is decreasing on the interval and it's a right endpoint approximation. Last but not least, we need to do a midpoint approximation. When we do that, we need to first figure out the base of each rectangle. That's b minus a over n, which again is pi over 8. We then need to figure out the height of each rectangle. So my first subinterval goes from 0 to pi over 8. The midpoint of that would be pi over 16. I then plug in pi over 16 for x in my function, and I get the height at that corresponding value, which is 0.981. So that's going to be the height of my first rectangle. The height of my second rectangle is based on the midpoint of that interval. So the midpoint between pi over 8 and pi over 4 is going to be 3 pi over 16. I plug that in my function up here, and cosine of 3 pi over 16 is 0.831. So that's going to be the height of my second rectangle. The third rectangle is going to have a base of pi over 8 and a height that is based on the midpoint of that interval between pi over 4 and 3 pi over 8, which is actually 5 pi over 16. I plug that in for cosine, and I end up getting approximately 0.556, which is going to be the height of my third rectangle and the height of my fourth rectangle based on the interval from 3 pi over 8 to pi over 2. I need the midpoint, which is 7 pi over 16. Plug that in for cosine. I get 0.195. That's going to be the height of my fourth rectangle. I then find the area of each of those rectangles, add them together, put that in my calculator. I get approximately 1.006 units squared. And that is the approximate area under the curve over that given interval. Now, is this an over or under estimate? Well, the graph is concave downward on that given interval. Therefore, this midpoint approximation is going to be an overestimate.